Okay, we had a minor glitch, so we had to do 2 separate videos for this. So what we're talking about, these examples are referring to, if you think about the example that we did back in the fall about tapping on the soda cans, that's kind of what we're using throughout these notes because that's where we left off when we stopped chapter 3. So if you want to work through with me and we'll go ahead and find the standard deviation together, I'm going to show you the table, so you can go ahead and be typing in this data in your calculator. You'll probably want to pause the video right here. But your time, your 0, 4, 8, 12 seconds, that's going to go in L1. So you'll do a 0 10 times, 4 10 times, and 8 and 12 10 times. And then this is the amount of soda remaining, so that's going to go in L2. So you can pause right here, go ahead and type this data in, and I'm going to continue on. So here is where my data has been typed in, and a couple of things you want to make sure of, once these are typed in, you do want to make sure your diagnostic is on. So if we go to second 0 and we'll go down, turn on diagnostic. Okay, and we want to make sure that our our plot 1 is actually turned on for right now. So that one's turned on, and then I'm going to turn number 2 off. So if yours are okay, then you can just leave them alone. Okay, so before you can do the residuals, you have to get your least squares regression line. If you do not get that least squares regression line, your residuals are not going to be correct. So let's go ahead and do our least squares regression line. Go to Stat. We'll calc number 8 and make sure that X list is L1, Y list is L2, and for the store reg, we do want to store it, so go to vars, over to Y vars, and enter. Okay, so there's our least squares regression line. All right, so now what we can do is get our residuals. So if we go back to Stat and Edit, we're going to go up and highlight L3, and we'll do second stat, and we're going to pick number 7 and hit enter. Okay, so this will give us all of the residuals for each data point. Okay, so if we want to do the standard deviation of residuals, what you can do here is, if you just go to Stat, Calc, we're just going to do 1 var stats and change it to L3 because we want, that's what we're using the residuals. And we'll calculate. So you want to look at this number right here. You cannot use standard deviation. It is going to be close, but it is not the exact same. So you cannot use either one of these for standard deviation. And like I said, when we actually do calculate this, plug into our formula, it will be very, very close, but there will be a difference. So you need to make sure when you're doing standard deviation of residuals that you actually use the formula. Okay, so like it says here, this is the number that we just got. So that's 951.32. Okay, so 951.32. So that's already squared. Now, we had 40 pieces of data. So if you look back here at the formula, 40 minus 2, n is the total amount of data, so that's 40 minus 2. We'll get 38. And, of course, we're going to take the square root of that. Okay, so if we type this in, just going to go back out to my main screen, square root of 951.32 divided by 38. So that gives us 5, and we'll just round it. Since it's 0.003, we'll just round it and keep it at 5. Okay, so if you go back, remember that was very, very close to the standard deviation that we got, but it is different. Okay, and it's because we're dividing by n minus 2 instead of n minus 1, and I briefly explained that difference already. So the standard deviation of our residuals is 5. So to interpret this value, so what that means is When we use the least squares regression line to predict the amount of soda remaining using the amount of tapping time, our predictions will typically be off by about 5 milliliters, okay? So that means any prediction is just going to typically be off by about 5. You know, maybe a little more, maybe a little less, but typically it's going to be about 5. That's how you can just kind of copy this sentence. Anytime I ask you to interpret standard deviation of residuals, you just say that that's how much it's going to be off by, whatever that number is, okay? So to continue on, suppose that, let's see here. Okay, sorry for the pauses. Sometimes the camera starts to freeze up. Something's going on with the connection, but anyway, we'll keep on rolling as we can. So this next part, suppose that we wandered in during the can tapping experiment and found a partially full can. Without measuring the contents, how could we predict how much soda is left in the can, assuming we had access to the data? So the first thing you would do is use Y bar first, which is just the mean of all of your, how much is left in all of the cans. So it's already been calculated, but basically this 264, if we go back to our calculator here, just real quick, remember if we go to stat and edit, this L2, that's how much was left in each can. So if we go to stat and calc and we do the 1 var stats again, I'm just going to do L2. Okay, so here is our mean. There's the 264.5. So that would be a good guess if we had, if we weren't going to measure it. So the average, we would guess the average because that would probably put us pretty close. So how much better would our predictions be if we knew how long it had been tapped? And so obviously knowing the tapping time is going to help us make a prediction. And what we're going to do is we're going to develop R squared, which is the coefficient of determination, and interpret as the decrease in sum of squared residuals when using the least squares regression line instead of the mean of the response variable. And we're not going to worry about doing that on Fathom. Okay, so what we're going to look at right now is we're going to look at the difference in the mean and our values, and we're going to get the standard deviation of the squared residuals of that number. So if you go back to your list here, if you go over to L4, and if we want to get the difference, we don't have to do it for every single one, but if we want the difference between the mean, which was the 264.45, and the original data here of how much was left, we can just type in 264.45 minus, and if we just do second 2, that's going to subtract and do those and hit enter. So here is the difference in all of those. So if we want to do the standard deviation of that, if we go to stat, calc, we're going to do 1 var stats. So you just make sure list 4 is here. Okay, so the sum of the squared residuals, which is the sum, that's what that stands for, the sum of the squared residuals. So that's where the 6,505.9 comes from. And then the sum of the squared residuals, the 951.3, we did that earlier. So if we go back, we did that right here in that part of the formula. So if you take these two numbers and if we divide these, so if we do 951.3 divided by 6,506, okay, that is actually going to give us 14.6%. Okay, so this is just doing it by hand. Now, notice how here it says an 85% decrease. So what this means in context by dividing these two, since we did the sum of the squared residuals of what was actually in our list divided by the difference in the mean, the sum of the squared residuals, like the difference in the mean there, this is how much information is unaccounted for. Okay, so 14.6 of the variation in the amount of soda remaining is unaccounted for by the least squares regression line. So that means least squares regression line, the line is actually going to give you basically everything except that 14.6%. Okay. The easiest way, I think, to this, that's just how the formula works to actually get R squared. This right here, that is actually your coefficient of determination. Okay, but this is working backwards. So if you want to, to obtain 85% from this number, you just do 1 minus. So 1 minus 14.6. So that's actually going to give us, thinking percentages. So it would be 0.146. That would give us 0.854, or if we just round that to 85%. So that means that 85% of the data is accounted for when using the least squares regression. So moving on, to talk more about this. So what is the coefficient of determination and how do you calculate and interpret it? Well, we just calculate it by hand. But what it is, it's the fraction of variation of values of y that is accounted for by the least squares regression line of y on x. So you can there's 2 sentences that we can say when it does ask you to interpret, and we're going to do a little bit of practice. It's pretty simple, and it sounds really confusing right now, but once we get down to it and actually calculating it, I'm going to let you just use your calculator and just remember these sentences in order to interpret it. So if you get what the difference is, like that, the 14.6% that we just got, you would say the sum of the squared residuals has been reduced by, so in this particular example, we would fill in 14%, 15%, when using the linear model relating y to x. But be sure to use context, don't just say y to x. So our y would be relating how much soda was remaining in the cans based on the amount of time that the can was tapped. So that would be your x. So just make sure you put in context. Don't just say y to x. Put in context. And I just made a note here. If you're using this sentence, this is the formula you're using, which is what we just calculated. So the other way, and this is what I think is the easiest, is to interpret, is to say that the percent, which is going to be your r squared, of the variation in your y variable, so whatever the y variable represents, which in this case was the amount of soda remaining in cans, is accounted for by the linear model relating the y variable, amount of soda remaining in cans, to the amount of time that the can was tapped. So just make sure you, once again, put this in context. And you can use the r squared. So if we go back here, so I did want you to know where the formula came from, but if we go back to calc, and we're going to do number 8. So let's change our list, L1 and L2, store reg bars, y bars. There's your r squared, which was that 85%. That's what we just found. That's what I would use, just because you can work it out. It comes up with your least squares regression as long as you have diagnostic turned on. If you don't have diagnostic turned on, these 2 numbers are not going to pop up. So you have coefficient of determination, and you've got your correlation coefficient. The r is the correlation coefficient. The r squared is the coefficient of determination. So make sure you do know the differences. The r is what we talked about in the fall, and that was basically, if you had your plot, so if you remember, drawing the circles and the ovals, we really talked about r and the residual plots and all that. So r is your correlation coefficient. R squared is the coefficient of determination. And once again, these sentences would be how you would explain and interpret those. So, and I've already touched on this, but how is R squared related to R? So the coefficient of determination is the correlation R squared. So when you see a correlation, square it to get a better feel for how well the least squares regression line fits the data. If you're given R squared, and you may be given some examples in your homework or on a test, that you'll be given R squared and you're asked to find the correlation. Well, just take the square root, but don't forget to consider the direction of association. Because if you take the square root of R squared, first of all, R squared, when it gives it to you, is always going to be positive because it's being squared. Anytime you square a negative number, it's going to turn positive. So if you take the square root of it, it is obviously going to be positive as well. But if you are finding the correlation, remember correlation could be negative depending on which way your dots are going. So real quick here, if we have a scatter plot and our dots are, doing that's going up. So it's going to be positive. But if they're going down like this, obviously those are going down, it's going to be negative. Don't forget, when you take the square root, put a negative in front of it for R. So don't forget, that small little fact, because R squared is always going to be positive. R can be positive or negative. And some other things. So R squared and S both measure how well the least squares regression line models the data. S is measured in the units of the response variable. So so here in this case, your standard deviation. You do use the units of measurement of whatever's in context of the problem. R squared is on a standard scale and typically use percents for that. Neither address form. And then what I would also do, you can look at page 180 in your book. Look at the example where it's talking about SEC football. Answer the questions before you look at solutions. Solutions are on the very next page, on page 181. These are not long answers. Once again, so you remember the beginning of chapter 3, they were not long answers. And these aren't either. So I've got one for us to do together, just a real basic one. If you want to pause the video and go ahead and look at that example, read through it, look at it. It'll give you a good understanding. Here's another one that we're going to do together. So if we're going to find the least squares regression, so first of all, this is the same data that you had on your test. It was the freshness of flowers and adding the sugar. So all I did is I took out the scatter plot and I'm giving you a table instead. And you have to find your own least squares regression line. So what we're going to do is we're going to go to Stat, we'll edit. I'm going to clear out all of these lists. Okay, and we'll type in our new data. So go ahead and be typing that in. If you need to pause the video, if I get to going too fast, just go ahead and pause it. Okay, so here's all of our data typed in, and sometimes if you're being asked to find the correlation coefficient or the coefficient of determination or standard deviation of residuals, they may not ask you for least squares regression. But in order to be able to get all of this stuff, you have to have the least squares regression in your calculator. So we're here, we're going to go to Stat, Calc number 8. Make sure you got L1 and L2 for your X and Y. Make sure you store it in your Y1. Okay, so here our value, or here's our least squares regression. So we're just going to write this down. So remember, this is a prediction equation. So y hat equals 181.37 plus 14.2x. And we could go through interpreting the slope and interpreting the y-intercept. So, basically, this is the y-intercept. This is how many hours you would expect the carnations to stay if there were 0 ounces of sugar added. And you would say for every ounce of sugar added, you would expect the carnation to stay fresh for, 14.2 more hours. So that would be interpreting the slope. Just a quick review of that. So the correlation coefficient, so that is R. So 0.9. So what does it mean? So that means that we have a fairly strong linear association. Okay, so remember, this was the shape. You know, this is the closer it is to 1 or -1, the more of that oval shape that you have. The more rounded it is, the closer to 0 it is. So the coefficient of determination, so r squared is 0.82. We'll just round it there. So think of that as 82%. Remember, we talk about these in percents. So if we follow our examples, or kind of the forms that I gave you on that other page, if you're using the one that I felt was the easiest, we would say that 82% of the variation in the y variable, so in this case, in the hours of freshness, is accounted for by the linear model relating hours of freshness to the amount of sugar in ounces added. Okay, so there's our sentence on how to explain the r squared. So find and interpret S. Okay, so remember, this is the part that we actually have to calculate because it doesn't give it to us. So we've got our equation here. If you go back to stat and we want to edit, we want to get our residuals here. So we will second stat number 7. We'll enter. There's our residuals. We want the sum of the squared residuals. So if I hit stat in calc, we're just going to do one of our stats for list 3. So here's the sum of squared residuals, so 674.07. And remember, we're going to divide that. We had 12 carnations. There was 12 containers. So 2 less than that is going to be 10. And we'll take the square root. So that's what we're actually going to calculate right here. So the square root of 674.07 divided by 10. So is going to be 8.21. Okay. So, excuse me. All right. So if we want to interpret that, we would just say when we use the least squares regression line, to predict the amount of time sorry about that. The flowers will stay fresh. Our predictions will typically be off by about 8.21 hours. Okay, so those are the basics of what this section is going to be on.